Hey everyone, welcome to the second video of lecture 9, and in this one we're going to be continuing our look at coordination complexes, this time taking a quick look at the coordination number, what the coordination number is, although it's quite self-explanatory, and then the shapes of the compounds or complex ions that can be made for each coordination number. And we'll take a quick look through all of them, but at the end I'll focus on the two most common ones which we'll need to know more about going forward for the crystal field theory lecture. So first off, what is the coordination number of a complex? And that's quite simply the number of donor atoms that are bonded to the central metal ion. So for example, we saw quite a few times the nickel hexa-aqua complex. And then for this, the coordination number then would be 6. And that's because, there are 6 waters. And these 6 waters, each individually bonded. So if you get me, each of them has an oxygen donor atom. The reason I say this is for things that are bidentate. So if we had the nickel with 3 of those ligands instead, this would still be a coordination number of 6 because the ethanoldiamine ligand has 2 donor atoms. So it's not how many ligands there are, it's how many donor atoms are coordinating. So yeah, bidentates have 2 donor atoms. So if you have 3 bidentate ligands, it's the same as just having 6 monodentate like water ligands. For the first row of the transition metals, this can vary from 2 to 8, and we're going to be looking at all the shapes from 2 to 8. But 4 and 6 are the most common. So I'm going to go sort of 2, 3, 5, 7, 8 first, and then we'll look at 4 and 6 at the end because, yeah, as I say, they're the most important, the most common, and what we'll be looking at with crystal field theory as well. And the final thing is how these shapes can be predicted. So the shapes of the complexes can sometimes be predicted by looking at the number of ligands involved and placing them in positions as far away as possible to minimize steric repulsions. Now there's something that this sounds incredibly similar to, and that is VSEPR. Something we've looked at a lot for predicting the shapes of compounds. It was taking the electron pairs and placing them as far away as possible to minimize repulsions. So this is kind of exactly like that. You won't have any lone pairs to worry about. But essentially you'll see a lot of the shapes are very similar. And it's because, you can predict them in quite a similar way. Like if there are 2, we're going to put them as far away as possible, so it's linear, which you'll see in a second. But we will see how, this is just a prediction. It can be quite limiting in the context of coordination complexes. So we'll start with 2, the coordination number 2. And as I said on the last slide, this is linear. It's because it wants to minimize repulsion, so those ligands are as far away from each other as possible. It's not such a common coordination number or geometry. It's mostly commonly found with the copper, silver, gold ions. And if you remember, these are, they form a triad. They're the coinage metals. So this is one group. They've got low charge density, which means, they're only a 1+ cation. But they're also like quite a large ionic radius. This charge is not very dense. So these coinage metal 1+ cations quite commonly form the coordination number 2, and these are a linear geometry. Coordination number 3 is actually not very common at all. You struggle to find many complexes. They're trigonal planar in geometry, which again is very similar to if we were predicting things with VSEPR. So we looked at BF3 was a good example. We used that a lot because it was a Lewis acid, and when we were talking about Lewis acids, Lewis's bases. And BF3 also makes the trigonal planar geometry. If you take this to coordination complexes, it's exactly the same coordination number of 3, trigonal planar geometry. It's nowhere near as common. There's a mercury triiodide complex ion shown here. Another example is this complex I've written here for platinum, and I put this in because it's platinum in the metallic form. So these complexes can form even without being a cation. So this is neutral platinum with all its electrons still there. So it makes trigonal planar, but it's nice to know that the metals don't have to be cations to form these complex ions or complex coordination compounds. So coordination number 5, this is where we start getting sort of multiple possibilities. So there are 2 that I've shown down here. There's Trigonal Bipyramidal, which is shown on the left. We've sort of got this trigonal planar in the middle, and then one above and one below. So you would get like 2 triangular pyramids, one on top of each other. And then square pyramidal as well, which is where the square isn't quite in the plane. They're pushed down a little bit, and then you've got one sticking up, and it makes this kind of a square-based pyramid. And what's important between these 2 with coordination number 5 is that the difference in energy between the 2 geometries is very low. So you can see here I've got both of the examples. They're both for the same complex. So it's nickel with 5 cyanide anions or ligands. And because the difference is so small, the geometry can be cation dependent. So this complex can form both shapes, and it really depends on what cation is balancing the compound, which determines the shape of the complex ion. Coordination number 7 actually has even more possible geometries. So coordination number 7 is rare for the first row. You won't see it too much, although we've I can't think of a single one. But as you go down the triad, so once you're in the second row and third row of the periodic table, it becomes more common. And that's the same with 7 and 8, like the bigger ones. They require more space for the ligands to be around. So that's why, if you remember, the difference in size between the second row and third row is negligible. But there is a jump in atomic radius from the first row of the transition metals to the second. So that's why you see these larger ones, 7 and 8, for the second and third rows a lot more than for the first row, because there is just a bit more space to fit so many ligands around. As I said, 7 has a lot of possible geometries. So there's a Pentagonal Bipyramidal, which I've shown on the left here. So this is again another bipyramid. You've just got 5 in a plane, so like a pentagonal planar, I guess, which you'd never get that on its own. But then it's got one on top and one below, so you've got this pentagon-based pyramid up and down. The capped trigonal prismatic, which is shown on the right here. So here we've got 3 up and 3 down, kind of making a prism with 2 triangular pyramids that the points touch, and then, although it's slightly distorted, one ligand coming out of the square face that's made here. And then one that I didn't manage to find a picture of is the capped octahedral as well. So this will be like an octahedron but 2 up. Actually, I can draw that for you. So I think it gives an example in the textbook of an iron-based complex. I can't remember which one it is actually. So this is an example of one from the first row actually. So with an octahedral, you'd usually have the square plane in the middle, and then one up and one below. But in the case of a capped octahedral, you end up with sort of 2 at the top. So it's kind of like an octahedron, but there's just another one chucked on the top. And the biggest coordination number we get to is coordination number 8. Again, not very common on the first row, much more common as you go down, which is why we're looking at this complex here. And the shape we get most commonly is square anti-prismatic. It is possible to get others, but they aren't discussed in the book, and to be honest, they're not common at all. So square anti-prismatic is what we see here. It's kind of like 2 square-based pyramids that meet at the point, except one of them's rotated 45 degrees. So cubic is theoretically possible as well, and that would be almost like how we see the body-centered cubic in the crystal structures, to give you an idea of what the points would look like. Basically, if you rotate this 45 degrees so all the ligands are above each other, so you've got a square on top and a square below. It's theoretically possible, but it's not been observed. This is due to the ligand-ligand repulsion. So you can imagine this ligand is much freer, having this gap underneath. Whereas if it was directly above this ligand, there'd be repulsion. So they just always revert to this square anti-prismatic geometry. Now these first that I've talked about, 2, 3, 5, 7 and 8, they're not as common, especially not for the first row. So it's nice to know them, nice to know what shapes they are. And it's nice to be able to see as well how the coordination number kind of links with the VSEPR theory to give similar shapes for the same reason, just minimizing repulsions. but we haven't looked at coordination number 4 and 6 yet, and they're the most common in the first row, so let's do that now. Now, coordination number 4 has two important geometries, and we're going to look at these in much more detail in the crystal field theory lectures, or videos in that lecture. And they are shown here. So you've got tetrahedral, which is exactly the same as if we had 4 bonding pairs in the VSEPR theory. Tetrahedral, and square planar, which is quite a peculiar one. I don't think we've seen anything with a square planar like geometry yet. It's certainly not predicted by VSEPR, and you wouldn't imagine it to be stable, but it is seen quite a lot. Tetrachlora complexes, which are what are shown here, can adopt either of them, and it depends on the nature of the metal ion. So we'll talk about this a lot more in the crystal field theory lectures. But essentially, you can see here that cobalt chloride chooses tetrahedral, platinum tetrachloride chooses square planar, and we're actually going to look at this in more detail with crystal field theory, like why this electronic configuration and what metal center it is makes a difference. And finally, we've got coordination number 6. And this is one we're really going to be focusing on because it's the most common coordination number for first row D block complexes. You might have noticed, just even as we were going through some of the earlier videos with naming and stuff, we kept looking at complexes and complex ions that were like a cobalt, hexaaqua, nickel, hexamine, things like this. It was always 6. And that's because it is the most common coordination number for first row D block complexes. So for example, if you were to take any of the first row transition metals and make the complex with water, it would always be a hexaaqua and have this octahedral geometry that's formed from the coordination number 6. And because this one's so important, it's going to be one of the geometries we really focus on going forwards, especially in the crystal field theory lecture. We're going to be looking at how the molecular orbitals or atomic orbitals change when in this sort of octahedral geometry, how the electron configurations actually work, and where the electrons get placed in these orbitals, because that'll have a massive effect on things like color and magnetic properties. Octahedral is a really important one to know, but thankfully it's also one of the simplest, I think. So it's quite nice if you've got coordination number 6, which is really common. It's an octahedron. It's just 4 in the middle with 1 up and 1 down. So they're all the coordination numbers and the most common geometries anyway. But the ones that are super important to know are coordination number 4 and 6. So tetrahedral, square planar and octahedral, because we'll be looking at them in much more detail in the next lecture as well.